In this chapter, we will talk about nulls and alternatives, and it's very important to understand exactly what we mean by a null and an alternative. The null is the value that we are testing. We will talk about the center of the distribution being the value we believe to be true, and that's the null, what we start out believing. The alternative is what you want to show evidence of. Think about an alternative as a fact-based claim. So when we reject the null, we show evidence for the alternative. We say, I believe that I actually have enough reason to believe this alternative given the evidence. Alternatives are oftentimes evidence-based claims, where the null is what you start out believing until given evidence otherwise. So this prime minister has problems with his negatives. People don't like him. So currently he's probably around 78%, and they want to bring the negatives down. So this TV ad comes out and they say, well, we're going to make an ad for you and we're going to bring your negatives down. Who's making the claim? Sounds like the TV ad is, because they're going to say, we can bring down your negatives. So with that in mind, if the TV ad doesn't work, then they would stay equal to 78%. If the TV ad does work, they're going to go down. Now, when we have a null, in this class at least, it will have an equals sign. When we have an alternative, it'll give direction to the claim. Less than, greater than, or does not equal to. There are only 3 alternatives when we do a test in this class for testing a population parameter. Going down to the next one, in the 1980s, 16% of people obtained a bachelor's degree. So we want to see if that's changed. To test this, we will start out by assuming it is still equal to 16%. Because let's show evidence that it's changed. So with this in mind right here, let's put equal. And people would say, well, wait, it's probably gone up. But an important thing to notice is you always have to read the question. Read the question to find out which direction the claim is going. Is it going one way, up or down, or is it going both ways? The word changed means, is it different? Is it not the same? Any one of those wordings would mean not equals to. When we look at this question right here, motivational tape sellers want people to succeed at something. So usually only 19% of people who try to stop abusing alcohol succeed. So if this tape doesn't work, what would happen? Well, the true proportion of people who try to stop abusing alcohol would still be equal to 19%. But if it does work, the true proportion of people who try to quit would be greater than. Remember, the alternative is always some claim we're trying to show evidence for. If you're trying to say that some drug you're putting on the market helps people, well, that would be your alternative. My drug is better than the current drugs on the market. That is your alternative that you would need to show evidence for. If you work for Nike or Adidas and you want to show my shoes are better than the competitors, your claim would be that they are equal to the competitor, and your your null would be that they are equal to the competitor, and your alternative would be that they are better than the competitor's shoes. So remember, anytime you make a claim that needs evidence, if you're trying to state something is better or not equal to, you are talking about an alternative. When we talk about p-values, we're talking about the probability of our results occurring given the null is true. So let's look at this right here. If the null is true, it'll be at the center of the distribution. Given the null is true, we would see random variation around it like this. Because let's think for a second that 3.9% is the true proportion of, and we'll use an example from later problems, of birth rates of twins for mothers. So if twins only occur 3.9% of the time, and we think about maybe for very young mothers, what would we expect to see if for most mothers it's 3.9% of the time? We'd expect for very young mothers for it also to be 3.9% of the time. Now, of course, this has a very small standard deviation because we're looking at a large sample size. But at what point would you start to doubt that maybe the birth rate's more, or maybe it's less? When we look at the p-value, as we get further away from the null value, the p-value is going to get smaller. I'm going further away from it. Does that give you evidence for the null or against the null? As we get further away, we'd be less likely to believe the null. So when the p-value is low, we reject the null. When the p-value is low, we reject the null. Think about it. If the birth rate of twins for very young mothers is something like, I don't know, 64%, you can barely even see this p-value. The p-value is 0.0036, which this means there's only like a 0.36% chance, a 0.36% chance that given the null is true, we would observe this. There's a very, very small chance, given the null is true, we would observe this. I'm going to reject this null. That's not true. I don't believe it anymore. And I'm going to show evidence for an alternative that the true proportion is greater. There must be some distribution over here that I can't see that actually we are drawing from, because I don't believe this is true. Now let's say we had landed down here at 4%. Do you think this is true? Well, the probability that we would observe our results is about 45%, or results more extreme. There's a 45% chance that it'll rain today. Well, that seems possible. So I think this null is true because it has a 45% chance of occurring given the null is true. So we would not reject the null. We would fail to reject. One important thing is we only say reject or fail to reject, because in statistics we have evidence. We never accept anything. We either show evidence or fail to show evidence or show a ton of evidence or show a ridiculous amount of evidence, but we never accept something because accepting means that we know it's true. The antonym of reject is fail to reject, meaning that when we reject, we have enough evidence to go against the null. Somewhere over here, according to 0.05, this would be enough evidence. When we fail to reject, we do not have enough evidence to go against the null. We would still retain the null. Once again, when we are close to the null and the p-value is big, we're saying the probability, and this is a very layman's way of stating this, and this is not a book definition, but you can basically look at this value down here as the probability the null is true. There's a 45% chance the null is true. Right here, there's only about a 1% chance the null is true. If there's a 1% chance the null is true, I would reject that null. In conventional statistics, you will reject the null when p-value is below 0.05. We often call the rate of rejection alpha, and you'll see that on a later question. So going back, because I know you want to see some answers, the answer to this question is, our results or results more extreme would occur 6.7% of the time due to natural chance sampling variation. That is what we were stating right here. Our results or results more extreme would occur 16.7% of the time due to natural chance sampling variation. That is what a p-value is. Going on further, we can actually run some tests right here. So this is where your calculator comes in great use, but I beg of you to work these problems by hand. Working them by hand ensures you know how to use the formulas and gets you acquainted with the summary statistics we use for running these formulas. People who rely purely on their calculator can get very confused on test 3 because there are a lot of formulas and there's a lot of calculator functions. So work the problem by hand and do it on the calculator and you will set yourself up for success on the test. Right here, we're looking at a school where the students with perfect attendance is 45%. With this in mind, their figure has slipped to 44. The school officials will note any change. Our null will be that it is equal to 45%. Now it's very important you notice this is what we observed in the past. This is what we are observing now. So this is p hat. This is p naught because in the past This is what we observed, and we are now going to test this. This is the tested value. This is the sample value from 7,950 students. When we do this test, do we want to do not equal to, greater than, or less than? Think for a moment. We want to do nope, different than, which is not equal to. The reason being is we are asking to see if it's changed. Has it changed? We come up with the question before collecting the data. They want to see, has our perfect attendance changed this year? We don't collect data and then say, which p-value gives us the most evidence? So let's go ahead and look at some assumptions. We have randomization and independence, which are often grouped together, and this problem states they were collected randomly. Somewhere, there we go. It doesn't say independent, but we will assume independence just means we did not select couples or go to a lunchroom table and say, oh, let's randomly select this table, because there might not be some independence among those samples then. A lot of times randomization and independence goes together. If you have one, you generally have the other, and the problem should be a little more specific, so I don't like it in that regard. The 10% condition is satisfied, even though 7,950 seems like a lot of students. This must be a very large school or a school district. Oh, it's nationwide, so yeah. With that in mind, success-failure condition would state that we have at least 10 expected successes and at least 10 expected failures. 45% of 7,950 and 55% of 7,950 would state that we have at least 10 expected successes and 10 expected failures. So definitely met there. Perform the test and find the p-value. This is very important. I'm going to display the equations with some dummy numbers in them. This here is Q naught. When you do this, you would plug in 0.44 minus 0.45, because p hat is our sample proportion. P naught is our tested proportion. Down here we have 0.45 minus, and then this would be 0.55 because this is Q naught in here. 1 minus P naught is Q naught. And then we would have over our sample size, which is 7,950. Sample size goes down here at the bottom. Right here, sample proportion, tested proportion, assumed or null proportion, all the same thing, and then sample size. And we solve out for a z-score. Why is it a z-score? Because at the center of our distribution is P naught. And let's look over here. Let's actually do this by showing the math. We are testing the mean of 45%. We expect to see 45%. We need to do now P naught times Q naught over n square root. Punch it into your calculator. And over, what was my n? My n was 7,950. And we need to square root this answer. P naught times Q naught over n square root. I get a very small, never hurts to carry out quite a few decimals, and there we go. We can see 44% is somewhere in here, and we know 2.5% is below here and 16% is below here. So we're between 2.5 and 16%, probably closer to around 3%. We can actually observe this right now by going to below, outside, because we're running a two-sided test, and put in 0.44 and 0.46. Why am I putting in 0.46? When we run a two-sided test, we need to double the p-value. So if I had just done below, we would observe just the one-sided test, and we would get a p-value of 0.036. When I do the two-sided test, we double it, and if you notice, this value of 0.0365 is now doubling right here. Watch the tails up here as it goes from one-sided to two-sided. We are doubling, just inflecting it. I put in 0.46 because that's 0.01 above and 0.44 is 0.01 below. Now, you could simply just find the p-value of the less than test and double it. What would be the p-value of the greater than test? To find that, we can put in 0.44, which is where we landed. I'm putting in where we landed. If you notice, the p-value for the two one-sideds add up to 1. Because all you're doing is shading above or below where you landed. We landed at 44%, so to do the above test, I would shade above it, and to do the below test, I would shade below it. And think for a second. If you land below 45%, would you have more evidence that the true proportion's below or the true proportion's above if you land below it? Well, if you land below it, your most evidence is going to be for below. And when your p-value is small, that means you have more evidence because this was not likely to occur. Remember, the p-value, in layman's terms, is the probability the null is true. There's only a 3.6% chance the null is true. And that doesn't look likely. But for our test, we need to double this. And we get to 0.073. And funny enough, we would actually reject the null for the one-sided test and fail to reject it for the two. So that could come into play, you never know. Remember, the two-sided test is always double your smallest one-sided test. So here's our smallest one-sided, now there's the two-sided. So let's go ahead and find what would be our z-score. Our z-score is the difference in terms of standard deviations. And look, one standard deviation, two standard deviations. Z-score is 0, -1, -2. And the equation states find the difference. The difference between 0.44 and 0.45 is 0.01, negative. I do let's look at it. I land at 44%, and the null was 45%. That is a difference of negative 0.01. Then I put that in terms of standard deviations. Negative 0.01 divided by the standard deviation gives me negative 1.7922. That is about where I landed right here. I took negative 0.01 and divided it by the standard deviations. And that is the equation. The difference divided by standard deviations gives you a z-score. And we observe that right here. Difference in terms of standard deviations. So let's go ahead and enter this in and finish up this problem. So right here we want the p-value. The p-value for this test would have to be found via an applet or with your calculator. So you can go into the stat test button under stat test, punch in your null proportion, which was 0.45. For x, you have to type in 7,950 times 0.44. We are getting the number of successes. And my number came out as a whole number, but you have to round up or down if you get a decimal. For n, we need to enter in the total number of samples, 7,950, and then your alternatives are stated as not equal to, less than, or greater than, and we can hit draw, and you will see the exact same picture. If you are doing this, you will see the exact same picture you saw over here, and you will get the p-value you obtained down here. Here is our p-value, and you will see the same thing on the calculator. Work it on the calculator, and work it by hand when doing this problem. And you can't get the p-value by hand unless you want to have some calculus fun. And there is our p-value. Now, we are going to set alpha here to 0.05. This is when we would have enough evidence to reject the null. So in this instance, we fail to reject the null, meaning we do not have evidence for the alternative. When we reject the null, we show evidence for the alternative. When we fail to reject the null, we do not have evidence for the alternative. Right here, we just put all the assumptions into one. And do we have randomization independence? Yes, it looks like it says random on here somewhere. It doesn't say random. It should, but it doesn't, unless I'm missing it. We need to sample less than 10% of all teenage girls. That sounds like less than 10%. And we need at least 10 expected successes and at least 10 expected failures, which would be 3.8 times 544. 10 expected successes and 10 expected failures. And I don't like that they don't mention randomly selected or independently selected. The problem should state that, and on the test, it needs to state that to be true. So, bad quartz compass. When we look at this question right here, we want to see if it is different. So with this in mind, they're asking, is it the same? So the null would be The true proportion of twins born to very young mothers is equal to 0.038. The alternative would state that the true proportion of twins born to very young mothers is not equal to 0.038. It is very important you can write out nulls and alternatives just like this. These test questions have killed people in the past. We just say write the null and alternative and people have no idea what to write. So what are we testing here? We are testing the true proportion to see if it is equal to some null proportion. This could be stated as P0 right here. 0.038 is the value we are testing, P0. And if you look at the equation, we are testing P0. We are finding the difference from P hat to P0, and the distribution we created is centered around P0. That is the value we are testing, and that is why you see it in the equation right here, and at the center of this distribution will be P0 again. So let's go right here. To get the z-score, we need to do the exact same thing. Put 0.038 in right here, and find the standard deviation by doing 0.038 times Q0, which is 1 minus 0.038, so 0.962, and then divide by the sample size. For this problem, that is 544. Then we need to do second square root, second answer, and we get 0.00819. Now we have the distribution. Here is our distribution, and it's very tight around this. The standard deviation is very small. We need to find some value to test now. Our tested value can be found by getting p hat. P hat is merely the sample proportion of successes, which is 13 over 544, x over n. 13 divided by 544 gives us 0.02389. So let's go below 0.02389. Now this is not the test we are running. This right here is a one-tailed test. But how in the world could we get the p-value for this? We could obtain the p-value just by doubling this. Very long number. It's basically 0.0425, which when we double that, we get 0.085. We just double this. Just imagine an imaginary tail over here. With this in mind, let's find the z-score. Well, the z-score is just how many standard deviations we landed below the assumed value. And it looks like the z-score is about negative 1.7 again. So let's take the difference here. The difference in our value can be obtained by p hat minus p0. So 0.02389 minus 0.038. We get a difference of negative 0.01411. That's the difference right here. Now put that difference in terms of standard deviations. Divided by 0.00819,747. I just added in a few more decimals. That difference in terms of standard deviations is negative 1.7212. We're just finding out the z-score of this. How odd is it? It's kind of odd, and it's pretty odd in my opinion when it's a less than test. But when we double it, it's not going to be as odd. And let's go ahead and find out that double value. If we want to look at what you will see on your calculator here in a second, you should see something, if you're doing my example, something similar to this right here. Making sure I get the right answer. 5. Let me just add these. Want to make sure everything is done correctly for you guys. 5, 2. It's like I've got a calculator right in front of me. Why don't I just get the answer? There we go. Now I have found the value on the other side that is equal distance and doubled it. And if you notice, the p-value I stated before is simply double it. There's some decimal differences just because of me not carrying everything out here. But when you look at this, you can see it double itself right there. So we have the one-sided less than test, and we have the two-sided does not equal test. So let's go ahead and start putting in some answers. The z-score for this was negative 1.7 0.772, and that's right. Make sure to put in your negative or positive there. Well, positive is assumed if no value is given. The p-value for this, we obtained this, and we're doing a two-tailed test, is 0.08. Is it 4 decimal places 5? And does it like it? Yes, it loves it. There we go. Now we're going to use an alpha of 0.05, and it doesn't tell us that. Why would it not tell us that? We can pick whatever alpha we want. I want to use an alpha of 0.10. I can reject. You can pick when to reject by setting your alpha. And we'll talk more in the next chapter about what that kind of does or to your problems. But with a conventional 0.05 alpha, which is assumed unless stated elsewise, we would fail to reject right here. That would state that the true proportion of twins for teenage mothers is not different, which is the null. You failed to reject the null. Think about what would have happened if we landed further away. If we had landed at something like 20%, or excuse me, 0.02%, 2% rather. If we had landed at 2%, then reflecting this upwards would have given us 56%, and yes, our p-value is very small. We landed further away here, so we are going to reject the null. If we had landed really close to the null, we would definitely not reject, because we landed right here. Well, the null looks to be true. Remember, the p-value is the probability the null is true, in layman's terms. With that in mind, we will reject the null when there is a very small probability it is true. So our p-value of 0.085 does not meet below 0.05. We fail to reject. Good luck, and make sure to understand this chapter because it is definitely a building block for the rest of the final test. Good luck.